In this section, I'm going to focus on choosing policies. So the previous module did a high-level overview of all four classes of policies, but how do you choose among them? That's the topic that we're going to cover right now. So the way we write out this problem of searching over policies is we have the step of usually a human thinking about the four classes of policies. There's a lot of subject to judgment. We might think about various hybrids. Most humans use hybrids in many situations. And then we have the problem of searching over the tunable parameters. Now, how we go about choosing policies, it helps us start by asking some basic questions. Does the problem suggest an obvious rule or relationship, buy low, sell high, order up to, inventory replenishment, that suggests a PFA? Now, maybe you want to throw out at a big linear model or even a neural network, but always look at the problem and say, is there any natural structure? For example, now think about, does a greedy policy where you ignore the future make sense? There's a number of problems like facility location where they'll just act on a static model. Always look at the simplest policies. Is the problem fairly stationary? This might lend itself to a policy that does not need to directly plan into the future. Does the problem seem to require planning into the future, such as planning a path to the destination? DLAs and possibly value function approximations are probably needed. And does the value of being in a state suggest structure, convexity, monotonicity, linearity that can be exploited? I mean, always sit down and look at your problem and ask, what type of structure is there? Let me consider this basic inventory problem. This was a great application. I had a lot of fun with this. This is a problem where we have to satisfy the energy load of a building. We can pull energy from the wind farm. The supply is highly variable, but it's free. But I can always pull energy from the grid, effectively for this problem in infinite capacity, but the price is highly stochastic. I mean, when I say stochastic, I'm talking about it can go up by a factor of 20 to 100 over a base price. Grid prices are highly volatile. I have a battery storage device that helps me smooth over variations. I can get through low wind periods by storing high wind if it's more than I needed. So with my postdoc at the time, Stefan Meisel, we created 5 variations of this problem. And we didn't do this at random. We knew what we were doing. We had created 5 policies, 4 from each of the 4 classes, plus a hybrid. Now, the number in the square indicates how well it's doing, and yellow means this is the best of the set of policies. Notice how each of the 5 policies was made to work best on one of the different problems. Again, we knew the strengths of each of the policies and were designing problems to match up with the strengths of the policy. But it indicates that you can't just arbitrarily assume that one policy works best or certain policies work best most of the time. There are going to be problems like planning dynamic routing over a transportation network. You have to plan into the future. There's going to be inventory planning problems where you can just react, and then other ones where you have to do forecasting. We've also got this issue of the different ways of evaluating a policy. And when you look at all of these, which are absolutely important in a real-world setting, you sort of wonder why people even talk about an optimal policy. I think that's just something of interest to mathematicians. Now, I'm going to take my 4 classes of policies and subdivide class 4. I'm going to take class 4 and first divide it between deterministic look-ahead and stochastic look-ahead. And then I'm going to take the stochastic look-ahead and divide it between where a decision is a discrete action versus where a decision is a vector. So this is 4 different types of policies based on the problem. Which ones are the most useful? So this next slide took me a career to write down. Category 1 consists of 3 types of policies. PFAs, the policy function approximations, CFAs, which are parameterized deterministic optimization problems, and deterministic DLAs. Now, deterministic DLAs and CFAs tend to look the same. They're both deterministic optimization problems, but a pure CFA does not plan in the future, where a deterministic DLA does, like Google Maps plans into the future. Um, Category 1 is absolutely going to be the most uh, commonly used sets of policies. These are the policies that all of us use in everyday life to make decisions. Now, Category 2 arises when we really have uncertainty in the future. And let's assume that we have problems where it's a discrete decision, do something or not do something, or do one of a finite set of choices. And I've got the uncertainties that often arise in practice. So this is an important problem class. There's a number of books that cover decision trees, which are a fairly powerful way of handling Category 2. Now, Category 3, this is when we use Bellman's equation. This is when we're trying to compute value functions, usually with approximate dynamic programming of some form. And I put this down in Category 3. It has gotten a tremendous amount of attention from the academic literature. I have a 600-page book on this topic. But after many years and looking back over the book and the methods that I actually found most useful, I've put this down on the list well below Category 2. It's a very powerful strategy for a very small number of problems. Now, Category 4 is when we not only have uncertainty, the decisions are vectored, and there's a strategy called two-stage stochastic programming. There's a pocket community in operations research that likes this quite a bit. My feeling is that it has very few real-world applications. These are very hard to solve. They're not exact. They make major approximations that possibly can work well in some settings, but otherwise don't. Now, let me come back to my bridge between machine learning and sequential decisions. If I look at PFAs, and if all I do is focus on PFAs, policy function approximations, all I'm doing is looking at the exact same set of functions that machine learning is doing. Take all of the linear lookup tables, parametric and non-parametric models, including neural nets, and if all I want to do is work on those, what's happened is that's PFAs. The only difference between machine learning and sequential decisions is machine learning needs a training data set, so I can fit my function to the data, and sequential decisions is using that function to represent the policy, and then I tune the policy to work well over many sample scenarios. But that's only one of the 4 classes of policies, and it's the simplest class. Again, it's fairly useful for many problems. It will never handle problems that are vector value. We then have the remaining 3 classes of problems that are all themselves optimization problems. They have embedded optimization problems, which is also what makes them amenable to solving high-dimensional problems, because I can use solvers for that. So what we're doing in sequential decisions is closely parallels machine learning. It's just much richer. Now, if you take machine learning, searching over functions, let's imagine that I'm sort of choosing between, I've got this linear function of relating demand as a function of price, or maybe I'm going to use a logistic regression, and I'm going to have my training data set to help me fit the function that I chose by hand, and then I'm going to use the computer to tune it to do the best fit possibly. Now, let's imagine that with parameterized policies, all I'm doing is looking at the Category 1, the PFAs, the CFAs, and deterministic DLAs, and these are all parameterized. So now I have to tune the parameters, and at a later time I'll show this exact problem, but I have some algorithm for tuning the parameters. What you can see is that within the most commonly used policies for sequential decisions, it closely parallels machine learning. It's just that it's possible that my parameterized function may be a deterministic optimization problem. So when you're choosing policies, take a look at your problem, and let's assume it's not something like chess or Go. It's an actual real human process problem. I tend to find the design of the policy and the design of the model is like a ladder, and you want to climb the ladder from simple to more complicated. And what you want to do is start off with a model, and generally you're going to start off with a simplified model, because we all do. You should start off with a policy that's suitable to the model that you've started with. But as you add realism and details to your model, you may have to add sophistication to your policy. And so you've got this climbing process from simple to more complex. So for more on policies, my website under policies has a particular web page just on this problem of choosing policies.